The question we are solving now belongs to test series 3. It is of network theory subject. In specific, it belongs to Laplace transforms and sinusoidal steady state analysis. As per the question, there is a sinusoidal circuit which is as shown in the figure. It has an excitation of V of S and the source carries a current of I of S. There are two branches connected in parallel with the voltage source, and the two branches contain the resistances 1 ohm and 1 farad and 2 Henry, 1 ohm and 1 farad. It is given that V of S leads or lags I of S by 90 degrees, then we need to find the frequency of operation omega if the operating frequency of the circuit is S is equal to J omega. So we need to find the value of omega such that V of S leads or lags I of S by 90 degrees. Please note that this is a common data question. So for V of S to lead or lag I of S by 90 degrees, the term Z of S is equal to V of S divided by I of S should have its real part as 0. If real part is 0, the imaginary part is the one which contributes the phase, which can be given as tan inverse of x by 0, which will be equal to pi by 2 or minus pi by 2 depending on the sign of x. So now let us find out Z of S is equal to V of S by I of S, or Z of S is the impedance as seen from the source terminals. So Z of S can be given as 1 plus 1 by S multiplied by 2S plus 1 plus 1 by S divided by 1 plus 1 by S plus 2S plus 1 plus 1 by S. This is due to the reason that as 1 ohm resistance and 1 farad capacitance are connected in series, the equivalent impedance is 1 plus 1 by S. Similarly, 2 Henry inductor, 1 ohm resistance and 1 farad capacitor are connected in series. Their equivalent impedance is 2S plus 1 plus 1 by S. So the impedance as seen from the source terminals can be written as Z of S is equal to this impedance multiplied by this impedance divided by sum of these two impedances. Now let us substitute S is equal to J omega, upon which the above equation gets simplified as 1 minus J by omega multiplied by 1 plus 2J omega minus J by omega divided by 1 plus 2J omega minus 2J divided by omega. This is upon substituting S is equal to J omega. Now we need to find Z of J omega such that its real part is 0. Now let us try out the values of omega given in the each of these options. So if we see the option B, it corresponds to omega equal to 1 radians per second, and for this value of omega, Z of J1 can be written as 1 minus J multiplied by 1 plus 2J minus J, that is 1 plus J divided by 1 plus 2J minus 2J. This upon simplification becomes 2. Sorry, there is a term S here, because of which there is a J omega term here. So this can be simplified as Z of J1 is equal to 2 divided by J, that is equal to minus 2J. From this we see that for omega equal to 1 radians per second, Z of J1 is minus 2J. It means that the impedance at omega equal to 1 radians per second is purely imaginary, and hence the real part is 0. So from this we can say that the value of omega for which the real part is 0 is omega equal to 1 radians per second, or omega equal to 1 radians per second corresponds to the condition that V of s leads or lags I of s by 90 degrees. Hence, the correct option representing the required conditions is B, and the option B corresponds to omega equal to 1 radians per second. Here we got the answer by substitution method.